It's good. Okay. All right, great. Well, thanks everybody for coming. This is our last plenary talk. It's been really wonderful having you all here. And I wanted to remind you to just pay attention to your email. In the next couple of days, we'll be sending out some closing items. But for now, our final speaker is Ian Biringer. He received his PhD from University of Chicago in 2009, where he was advised by Juan Soto. After finishing an NSF postdoc at Yale, then he joined the faculty at Boston College in 2012. He's received numerous awards, including the NSF Career Grant, and today we're very excited that he'll be telling us about the space of closed subgroups of PSL2R. So take it away, Ian.
Excellent. Well, thanks very much for the invitation. I mean, the parts of the conference that I've been to so far have been just amazing. So I'm happy to be part of it. Wait, so shall I go to 150 then? Is that the right amount? Yeah. Okay, cool. So yeah, so I'm going to talk about the space of closed subgroups of PSL2R. And as I mentioned here, it's a joint work in progress with Nir Lazarovich and Ariel Leitner. And so, yeah, I mean, okay, so it's going to be a work in progress talk because this is what I'm excited about at the moment, and because I don't know, it's kind of it'll end up being a long work in the end. You know, I think we're about to finish the first paper, and you know, that's already like 70 pages. So like, you know, I feel like I should be able to say something at this point. So yeah, okay. So we're going to talk about spaces of closed subgroups of various Lie groups today. And in particular, the original stuff's about PSL2R. So just to set up the problems. So let's let G be a Lie group. And, you know, a lot of what I'm going to talk about here, you can discuss in greater generality than just a Lie group, but I don't know, a Lie group is fine for this kind of talk, I think. And then I'm going to let like sub of G, so sub G, be the set of all closed subgroups of G. And so, you know, G being a Lie group has a topology. And so, you know, when I'm saying closed subgroup of G, I'm talking about this subgroup being topologically closed inside of the manifold G. Yeah, and the basic point of the talk is, you know, how do we understand this space sub G? And okay, I just called it a space, so there better be a topology on it. So what's the topology? It's sort of easiest to define what the appropriate topology is in terms of what it means for a sequence to converge. So I'm just going to do that. If you want to write down a basis of neighborhoods, you can do that too, but I think it's a little less intuitive. So I'm going to say that a sequence Hn goes to H in sub G in the Chabauty topology. If the following two conditions hold. Okay, so this is supposed to be some sort of like visual convergence of these subgroups within the group G. And so what that means is that, you know, first, any if you take any element of the limit group, then this should be a limit of a, you know, sequence of elements Hn in Hn. Okay, so anything in the limit group is a limit of a sequence from the approximating groups. And two, I want so any accumulation point of a sequence Hn in Hn to lie in H. Okay. Right. So this is the definition of convergence in the Chabauty topology. And I think it's useful. I mean, I think just to understand this notion of convergence, we'll just do some examples. So, you know, the first example maybe you should think of is G to be just the real numbers here, equipped with addition. That's the group structure. So then what's sub G? Okay, we'll just like think set theoretically for a second. So what are the closed subgroups of the real numbers under addition? Okay, well, there's the whole real numbers. That's definitely a closed subset, and it's a subgroup. And then I've got so I've got the integers, and I also have all like all cyclic subgroups. So these are just like things generated by some real number, which I can take to be positive if I want. And then there's also just the trivial group. So then you want to understand, okay, well, that's set theoretically what sub G is. What's the topology though? And so the topology here turns out to be the same as it turns out to be just a closed interval, which I'm going to write as the closed interval 0 infinity just for easy parameterization. And the way that you imagine this is, so I'm going to just write, the closed interval 0 infinity like this. And then the homeomorphism here takes R to 0, takes 0 to infinity, and it takes, the subgroup AZ to just the element A. Okay, and what you should think of here is that as you take A to 0, for instance, what happens to these groups AZ? So these are like the groups generated by A. And so these subgroups, AZ get denser and denser in R. So in the limit, if you start taking limits of sequences from these subgroups, then you can get any real number. So that's why, like, as A goes to 0, the subgroups AZ are converging to R, which is sort of the content in that picture. And so AZ is going to R. And then as A goes to infinity, well, okay, so imagine what's happening. So you're taking the groups AZ as A goes to infinity. And so all the non-zero elements of AZ sort of get farther and farther away. They sort of disappear off into the distance as A goes to infinity. And so in the limit, all you get is just the 0 element. Right, so all you see is 0 in the limit. Okay, so that's like a complete description of sub of R. Make sense? Okay. So, all right, so we did R. So what's natural to go to next? Maybe I'll do R2. So second example, G equals R2, again, just with addition. So, all right, so first thing you ask is like, what set theoretically is sub G? Well, here are now the closed subgroups of R2. I'm not gonna like sort of write them down completely like I did in the previous example, but they're all isomorphic to one of the following groups. So they're all, so you have the trivial group, you've got R2, so you can also have just a copy of Z inside of R2, just generated by a single vector. Okay, I could have a line through the origin, which is gives me a copy of R inside of R2. I could also have a copy of like R cross Z. And then I can also have something that's isomorphic to Z squared. And these latter ones are called lattices. All right, and then you have lots of interesting limits. Like what's something that I could draw? Well, you could do something that like okay, maybe the first element of my sequence is some z squared that looks like this. Okay, but then maybe the next element of the sequence, like in one direction, the points start getting closer together. So I get something like okay, I can still make a lattice that looks like this. And then you just have them keep getting closer and closer together in that direction. And then, in the end, you'll get something that's an R cross C. Okay, so I can have like a sequence of lattices that converge in this space to an R cross C. Right, and of course, you can also make sequences of lattices that converge to, really to whatever you want. The lattices are going to be dense in this space. Right, so if I start spacing out all the points in the lattice more and more and more and more, then in the limit I sort of converge to the trivial group. If I make the lattice extremely tight, like filling out R2, then I can make a limit that's R2 in the end, et cetera, et cetera.
Maybe I missed something. Are you forbidding torsion, or?
Well, so the group is R2, like with addition.
Understood.
Yeah. So there's no torsion. So yeah, and so this is the first. I don't know, I really love this theorem. So this is so in fact, okay, so you have this sort of complicated description of what sub of R2 is then. I mean, if you can call this a description. But in fact, you can characterize what the topology is. And so it turns out, so this is a theorem of John Hubbard, and it's a theorem of Hubbard, Boretta, from, I guess, 78, I guess. And so they say that sub of R2 is homeomorphic to the 4-sphere. And then moreover, let's say that you set N to be the set of all non-lattices. Okay, so remember we had all these different possible isomorphism types of groups, and one of those isomorphism types was z squared. So N is just everything that's not isomorphic to z squared. Then, okay, so I look at that as a subset of sub of R2. Then the theorem says that if I look at the pair sub of R2 with like N inside, then this is homeomorphic to should I write it? Maybe like this is homeomorphic to like the suspension of the pair S3 with the trefoil knot inside. Okay, so, right. So I guess the content here is that this is if I take the suspension of S3 with the trefoil inside, like the trefoil suspends to a 2-sphere. And so I'm saying, part of what I'm saying is that N is a 2-sphere. But I'm saying more than that. I'm saying that the way it's embedded inside of S4 is as the suspension of the trefoil. Okay, so right, and particularly this is sort of like this is not a tame embedding of S2 into S4, right? It's because you have the cone points of the suspension. All right. Yeah, this is I love this result because it sort of indicates that there's already kind of interesting topology in sub of R2. Like how much easier could you get?
Ask a question.
Yeah, what's up?
Can you say more about the cone points? Like what's happening in like the picture you had above? Is there a way to like say more about those cone points or something?
Yeah, I mean, I guess so. I think it's just about the actual points. Right, so what are the cone points? Let's see. I mean, I think that the best way to view the
Are the cone points not just 0 and R2?
the cone points are, yeah, I guess they're, yeah, no, that's right. I think they are 0 and R2. And I think the easiest way to view the kind of, I think the way that you should visualize the suspension is to say that, yeah, like where do you see like the trefoil coming in? So, right. So if you look at just the lattices, so I guess part of what I'm saying here is that the lattices should form like a suspension of the trefoil complement. And the way that you see the lattices, I guess, or the way that you see a trefoil complement here is that if you look at the space of like unit area lattices, then you know it's pretty quick to see that unit area lattices correspond to like SL2R mod SL2Z, which is like the unit tangent bundle over the modular curve, which is a trefoil complement. I mean, you can see that in a couple of seconds using separate fiber theory. So yeah, so you have like the 0 and R2, which are these cone points, and then you have the yeah, and then sort of interpolating between them, you have this right. Well, you have this suspension of this thing in the middle, which is like the unit area lattices, if that makes sense. Cool. So that's the Hubbard-Pereza theorem. And you know, maybe none of that made sense, but like if it didn't make sense, like one thing you can try to do is just go through and verify that all the dimensions are what you think are what they are here. Okay, so like go through and you can see pretty easily that the space of lattices is 4-dimensional, right? Because you need, how do you determine a lattice? You pick 2 generators. For each generator, you have 2 degrees of freedom. So that at least is comforting if you're expecting it to be S4. And then you can see that the space of non-lattices is 2-dimensional by going through all the cases separately. And then, yeah, start playing it around with it a little bit more. And, I think you can start to see parts of this picture. All right, so that's the case of R2. And then maybe just some remarks. So in higher dimensions, so it turns out that sub of Rn isn't a manifold. But so it's a stratified space in a certain sense, and is simply connected. So this is all work of Benoit Klockner, I guess from 2009. Okay, and so what the stratified space here, I mean, you're seeing the strata, right? The strata, if I look back at the sub R2 picture, then like you have all these different isomorphism types for groups, right? And if I fix an isomorphism type, then it's easy to parameterize what all the groups are with that isomorphism type. And that'll give you some sort of, some manifold inside of your space. And then if you look at all the different isomorphism types together, then all these manifolds fit together in the structure of the stratified space. You know, and he has this really nice, I mean, you know, it's a nice, pretty elementary paper where he you know, notes that it's not a manifold for except in you know, for n equals 1 or 2, and you know, shows that it's simply connected. So, right. And maybe just another remark, because I think this is really cool. So you can also consider so you can take the same topology, but just in a more general setting. So so I can take like C of X, just the set of all closed subsets of X. Right, and then there's this lovely theorem that says that, well, if I just look at at all closed subsets, now there's no group structure anymore. Then there's this great theorem that says that by Curtis and Shorey from '74, they show that you know, when X is a non-degenerate piano continuum. So what, I mean, what does that mean? That just means that X is compact, connected. Oh, here, yeah, X is just an arbitrary metric space. I'm sorry, I didn't write metric space here. So I'll write it here. Compact, connected, locally connected, metric space with at least 2 points, then the space C of X of all like closed subsets is homeomorphic to the Hilbert cube. Okay, it's the countable product of 0 ones. So, I mean, this sort of has nothing to do with the rest of the talk, but I just think it's nice. I mean, this is like an example of the wild world of infinite dimensional topology, which for the most part, this talk is not really about. And you know, in this, I guess in the case that I'm talking about here, then the topology that we're considering, this Chabauty topology, just becomes the Hausdorff topology on closed subsets of X, if you're familiar with that. All right, so, okay, but back to groups. So we've talked only about groups that are like Rn with addition so far. So, I mean, we should probably talk about more complicated groups. Yeah, and so I think the rest of the talk we'll talk about PSL2R. So let's let G be equal to, so really like, okay, we're going to talk about PSL2R, but that's the last time I'm going to say PSL2R. So really what I care about here, so those of you that know, there's this isomorphism between this group PSL2R and the group of orientation preserving isometries of hyperbolic space. Okay, and right, and you can get this through like the action by fractional linear transformations of PSL2R on the upper half plane. And so I'm just going to talk, but the fact that it's PSL2R is kind of irrelevant from here on. Like, we're just going to talk about the group of orientation preserving isometries of H2 and try to understand its subgroups. Right, so then, okay, so what can we say about closed subgroups of G? So it turns out that closed subgroups of G are either discrete so-called elementary. So what elementary here means is that they have a finite orbit. If you look at the action on hyperbolic space using its boundary, or they're the subgroup G. Okay, so it really doesn't matter if if you've never seen the word elementary before. I mean, I think you'll be able to follow what's going on without too much hyperbolic geometry background. But let me just give you some examples of elementary groups. So eventually I'm going to sort of describe, right, so if these are all the groups, they're discrete elementary or they're just the group G. Then to understand sub G, then I need to sort of describe the spaces of such groups sort of individually and say how they fit together. So here's so what are the elementary groups? So examples include, so maybe the first example would be, so the group A of gamma of translations, like all translations along a geodesic gamma. So the picture is, okay, so there's hyperbolic space, and there are things called geodesics in hyperbolic space, which are straight lines. And there are certain isometries of hyperbolic space that just sort of translate along, in the direction of this geodesic, and everything else around just sort of comes along for the ride. And then I can look at translations by any amount along this geodesic. And so that gives me, so because I can vary the amount of translation, this is giving me a copy of R inside of G. Okay, and that gives you, so that's one kind. I could also take the group like U of Q of all parabolic isometries, fixing some Q in the boundary of H2. So again, the point here is that there are isometries that, well, where the action on H2 kind of looks like the following. So so this point Q here is fixed. And then if you look at all like circles that are tangent to the boundary here and go through Q, then such an isometry sort of rotates around each one of these circles. So it preserves this foliation that I'm drawing here, and everything sort of goes around the circle that it's currently on. And I can vary again this sort of the amount that I push points along the circle to get again a group here that's isomorphic to R. Okay, so I fix Q and then I sort of vary the amount that I'm pushing things around these circles. And then you can also have something like the group K of P of all hyperbolic rotations around some P in H2. Okay, so this is this sort of similar thing, but now I've got some point P in H2 and I'm looking at the group of all rotations around P. All right, so then this is a copy of S1. Okay, and there are others. There are other elementary groups. And what are they? They're like cyclic groups, which you can get as cyclic subgroups of these R's. You can get some infinite dihedral groups, and you can get certain semi-direct products of R cross R, and you can get semi-direct products of R and Z.
And people are asking in the chat exactly what it means to be elementary or to have a finite orbit in the hyperbolic space.
Yeah, right. So right. So elementary means you have there's a like an orbit of your group. You look at your group, you look at how it acts on H2 union its boundary, and then you want there to be a finite orbit of this. So like for instance, here's a like if I'm looking at all translations along this axis, then this point is a finite orbit. This point is fixed by everything in that group. This other point here is also a finite orbit.
So it has some orbit that is finite.
Some orbit that's finite. Yeah, almost all orbits are going to be infinite, but there is some orbit that's finite.
All right, thanks.
Yeah. Okay. So there are others, but you can completely classify them, and it turns out that the topology on these on the space of elementary subgroups is completely understood. I mean, it's sort of something you can write down. Right. I mean, maybe just verbally, or maybe not verbally, because verbally is bad. So, e.g., if if you have like some situation where you have a sequence of gamma of like these geodesics gamma, or actually let's do it with the points P. So if I take like points P, P1, P2, and they converge down to like some Q in the boundary or something, then these groups K of like PI should converge to the group U of Q above. So there's a lot of sort of unsurprising stuff that happens with limits of elementary groups. And then, if you want to, you can even, you can kind of write down a complete description of the spaces, and here's its homotopy type. So there's a nice proposition, which, I mean, essentially this is due to Harry Bacon, Lucien Clavier from 2013. Although, I mean, the precise way that I'm going to state it is from our paper. They look at a slightly smaller space. And so the space of elementary subgroups of G is homotopy equivalent to the following subset of R3. So what's the subset of R3? Okay, so I'm going to start by drawing you a picture in R2, and then I'm going to transform it into a picture in R3 at the end. So take a circle that goes through 0 and 1 in R2, or yeah, in C, say. And then I'm going to draw, I'm going to draw this circle of radius 1/2, and then this circle of radius 1/3, and this circle of radius 1/4, and etc. Okay, so I get circles of radii going to 1, and then also the circle of radius 1. And then I'm going to take that picture and I'm going to make it be in R3 by making all these spheres. Okay, so now these are no longer circles, they're spheres. Okay, so what am I looking at here? I'm looking at a whole bunch of spheres. They all go through 0, and their radii are converging to 1. And also the sphere with radius 1 is in there too. Okay, so it's kind of like a wedge of spheres, except like the spheres are accumulating onto a limit sphere. Okay. And it turns out that's the homotopy type of this space of elementary subgroups.
Can I ask what the limit sphere is? That sphere with radius 1/2 there, the biggest one?
Yeah, the limit sphere is just it's just like the set of all K of P's. Like each K of P is a point in the limit sphere. And you get one p, you get one k of p for every point in H2. But then, right, this these get yeah. So I mean that's what the limit sphere is essentially in this Selma-W type.
Okay.
And so the other spheres essentially come from fixing an order of a finite group, and then letting the point that you're rotating around change. Okay, so that's sort of the situation with the elementary groups. And so now we have to just say a few words about the discrete groups, okay? And the discrete groups are the interesting ones inside of PSL2R and inside of the isometry group of H2. Like these elementary groups you can completely classify, but like if you start looking at discrete groups, then you're looking at all hyperbolic surfaces, for instance. And so just to formalize that, right? So a discrete group, gamma in G. So this acts properly discontinuously on H2, and so we can look at the quotient which is going to be a so-called hyperbolic orbifold. So this is X with, so X is the quotient of H2 by gamma. And okay, I mean, an orbifold is a slight generalization of a hyperbolic surface, where you're allowed to have sort of cone points. But if you haven't heard of orbifolds before, just pretend that I'm saying surface everywhere for the next 10 minutes. So if you have a discrete group, you can take the quotient by its action on H2. And then, if I fix some vector V in the unit tangent bundle of H2, say, and then you let, V hat in the quotient tangent bundle be the projection. Then you actually get a dictionary between discrete groups and so-called vectored orbifolds, right? So you get this bijection between all discrete gammas in G so all pairs like XV, where X is an, okay, I guess I need to say an oriented hyperbolic duorbifold, and V is a unit tangent vector. And I look at all these things up to an equivalence, which is by orientation preserving, vector preserving isometry. Okay. So, right, so the point is somehow that like a discrete group, you can look at the quotient, and if you fix a vector in H2, you can look at its projection and get a vector in the quotient. And then I'm saying that there's actually a dictionary between the gammas and then these orbifolds equipped with a vector. So if you want surfaces equipped with a vector, if you don't like orbifolds. Okay. And so the point here is that somehow you don't really need to do any group theory to start understanding discrete subgroups of G. Like what you can do is now you just talk about these hyperbolic orbifolds forever. Okay, so you've taken an algebraic problem and turned it into a geometric problem. Right, and so moreover, like the Chabauty topology, on the left-hand side corresponds to you know, I'm not going to write the definition totally here just because of time, but like some natural topology on this space of vectored orbifolds. And just as an example of the kind of convergence that you can see, imagine, okay, so imagine I have a sequence of like surfaces where maybe the genus is I or something. And this is, okay, this is my surface like xi. And then imagine my vectors are like vi here. And so the genus of this of xi is I here. And then if you let I go to infinity, then in this kind of convergence, what can happen is that you can end up converging to this, you know, one-ended Jacob's ladder surface that they've talked about in the infinite type mapping classes groups section. I mean, you get some, like, you can converge to some infinite genus surface. And the convergence is sort of visual, okay? So, I mean, so the idea is like you, so here, like xi vi is converging to xv. Right, so there's a way to visualize Chabauty convergences with this geometric convergence of vectored surfaces. Right. Yeah, and so then you get this nice description of what, you know, the different components of sub G look like. And it's a union of the following. So, right, so you get the space of elementary subgroups. And then you have, okay, then you have like all the groups corresponding to these vectored orbifolds. But you can sort of divide them up into different pieces. So like, let me just say how to think about the groups corresponding to vectored orbifolds, these discrete groups. Well, you know, for each, if I fix like some finite type hyperbolizable two orbifold S. So this is a topological two orbifold. So imagine, you know, for instance, like fix the genus 2 surface. Then there's a space like sub, maybe I can call it sub SG, which is all groups gamma where the quotient is homeomorphic to S and has finite volume. Okay, so I fix the topology and then I look at all groups where the quotient is homeomorphic to that. And so, you know, via the dictionary above, you can visualize this as like all pairs XV, where X is homeomorphic to S and has finite volume. So this is all like vectored orbifolds that are homeomorphic to S and vectored hyperbolic orbifolds that are homeomorphic to S. And this gives you some subset of sub G. And what is this thing? Well, this might seem kind of familiar because, you know, this is almost like talking about a moduli space. So here, and in fact, there's a sort of fiber bundle like this. So if I just look at like isometry classes of X's, not isometry classes of pairs XV, then I get the so-called moduli space of S. So this is just all like, oriented hyperbolic two orbifolds that are homeomorphic to S, mod, I guess, orientation preserving isometry. And then the only difference is that with this sub SG, I have V's as well. And how do you get the V's? You pick them from the unit tangent bundle. So you get this sort of fiber bundle. And so I think the correct way to think about the sub G is you have these three pieces. So you've got like the elementary subgroups, you've got all these sub SGs for different finite type surfaces S or orbifolds S. And then you also have, which will please people in the infinite type group here, just sort of a wild world of subgroups corresponding to infinite volume surfaces or orbifolds. Okay. And this is sort of this is in some sense the right way to think about sub G. Yeah, and then maybe I'll just say, if you're interested, you can ask for more details in the in the time afterwards. But like the main point of our paper is first, you can identify, say, the connected components of sub G. Like using this description, you can see how all these different pieces fit together, and you can right. So you can identify the connected components. And maybe I'll write the second part as like a conjecture. You can, this is going to sound really lame, but you can identify pi 1 of each component. Okay. So that's and so that's sort of the goal of the whole project is like to identify the connected components, which is not very hard, and then, but eventually I think we'll be able to figure out what the pi 1. I mean, we have sort of a sketch for what pi 1 of the whole thing is. And so this is sort of a first study of the global topology of this sub G. All right, but I'll stop there.
All right, great. So we're gonna have question time now. So if you have a question, just use the raise hand feature.